So, hello everyone. Let's solve one more problem about self-inductance. Let's look at the question. A direct current of 1 ampere is passed through a coil of 5000 turns and produces a flux of zero point 0.1 milliwebers. So there is, excuse me, so there is a coil of 5000 turns and there is a switch here and then some kind of voltage. So 5000 turns and the flux produced is given in the question zero point 0.1 milliweber and the current that is flowing here is 1 ampere. So initially this switch is in closed position, okay, and then the 1 ampere current is flowing. Okay. So what is the inductance of the coil? So it's quite straightforward. Inductance is nothing but N phi by I. So 5000 into zero point 0.1 milli divided by 1 ampere. So the thousands and milli will cancel. 1 is anyway there. 5 into zero point 0.1 is 0.5 henries. So this is the inductance of the coil here. What would be the voltage developed across the coil if the current were interrupted in 1 millisecond? Now, I open this contact. How much voltage will be appearing here? That is the question. So, so if I measure the voltage across the coil, so let's say I correct the voltage here, voltmeter to measure the voltage. If I interrupt this current, how much voltage it is going to generate? Let's do that. So what is the change in current? Change in current is final value is 0, initial value is 1, so minus 1. This is di. And what is dt? Okay, so change in time is 1 millisecond. So 1 millisecond. This is minus 1 ampere. And the EMF induced will be minus L di by dt. So minus 0.5 into minus 1 by 1 into 10 power minus 3. So the minus will get cancelled and then I can see that 500 volts is generated. It's a quite large voltage. So the lesson that we learn from this is that whenever an inductor is carrying a DC current, it is very dangerous to open the switch and suddenly interrupt the current in an inductor. Okay, so what would be the maximum voltage developed across the coil if a capacitor of 10 microfarad were connected across the switch breaking the DC supply? So typically what they do is if at all you are breaking the supply, parallel to the switch a capacitor is connected. So this is 10 microfarad capacitor. So under normal operation, let's say switch is closed. Okay. When the switch is closed, this capacitor is short circuited, so it has no role to play. The rest of the circuit will be unaffected. But the moment you open the moment switch is opened, the capacitor comes into the picture and then capacitor connected in series with the inductor. So the inductor already is having some energy stored in it. That energy is going to be transferred over to the capacitor during that instant of opening the switch. Okay. So let's estimate how much is the energy stored in the capacitor. So that is first energy stored in the inductor. So energy in inductor is nothing but half Li square. So this is half into 0.5 into 1 square. So that is 0.25 joules of energy stored. Now the same energy now will be transferred to the capacitor, energy in the capacitor. That is again half CV square. So again we have not seen the how these formulas are coming, but just as a time being you can understand that energy in the inductor is half Li square and energy in the capacitor is half CV square, where C is the capacitance, V is the voltage, and I is the current in the inductor. So now this is 1 by 2. C is 10 micro, so 10 into 10 power minus 6 farads into V square is equal to 0.25. So from this, I can calculate what is V. So what is the total voltage, maximum voltage achieved by the capacitor? So 0.25 into 2 divided by 10 into 10 power minus 6 whole under root. So little bit of simplification we can do. In the numerator I will get 0.5, and then into 10 power 6 I can take it to the above. So this will be instead of zero point 0.5 I'll take it 5, and then I'll put 100 in the denominator, and then this is square root. So 100 will cancel out, it will become 10 power 4. So it is root 5 into 100. Okay. So this is the answer. So what is square root of 5? Let's get the calculator. So 5 square root into 100. So I'm getting 233.6. So that is the 223.6 volts. So this is the voltage that is developed across the capacitor. So you just notice that in the earlier case the voltage was 500 volts. Now just because I have added a small capacitor, the voltage buildup is now restricted almost to about half of the voltage, that is 223 volts. So this way, by adding a capacitor across a switch, I can reduce the voltage that is being generated when an inductor is disconnected. So this is a short question. I hope you learned something from it. We'll see more in later videos.